Solving linear programs, a graphical approach. So let's look at that. The constraints of a linear programming problem define its feasible region. The best point in the feasible region is the optimal solution to the problem. For linear programming problems with two variables, it's easy to plot the feasible region and find the optimal solution. If there are more than two variables, we can't do it graphically. So you got to realize the point of this chapter is to understand strategically what we're doing and how to go about solving the problems, so that later when we can only do this graphically with two variables, but later when there's 30 variables, we know what Excel's doing and how Excel is going about, and it's not Excel, it's solver through Excel. We know how the computer is going about solving these problems and finding the optimal solution. So this chapter 2, we're kind of doing these by hand. We are doing these by hand. Plotting the first constraint. How do we plot this constraint? The first constraint, recall, is x1 plus x2 is 200. That's the pump constraint. So to graph these linear functions, the easiest way is I think it's called the substitution method. You put 0 in for x1, and what do you get? x2 is 200. So 0 for x1 and 200 for x2, that's 1 point, and you can see it's marked up there up at the top. And then we can do the reverse. We can substitute 0 in for x2 and solve for x1. In this case, it's real easy. x1 is 200, and then x2 is 0. So we can plot those 2 points, and we get those easy using the substitution method, I believe it's called. And I know this because I've been helping my 8th grader on this on these same kind of things for homework. So I know you guys get this. Once we have 2 points on this linear then we can draw a line through it, and there we have our line. So that's what we've done in this case. If we make 0 of x1, well, we have 200 pumps, we can make 200 of the other. If we make 0 of x2, we can make 200 of x2. And if we do something in between, let's say, and we can find any other point. If we substituted 100 in for x1, well, x2 would have to be 100 too, right? Because 100 plus 100 is 200 pumps. So the point 100 comma 100. So yeah, it would. That'd be in the exact middle of this line. Using the same method, this substitution method, we put 0 in for x1, and we get 0 times 9 plus 6 times x2 equals 1566. Well, we want to get the 6 out of there, so we divide both sides. It's an equality. We have to do the same thing to both sides. Divide both sides by 6. We get x2 equals 1566 divided by 6, which is 261. So 1 point is 0 and 261. Doing the reverse, substitute 0 in for x2, we get 9x1 equals 1566. Divide both sides by 9. 1566 divided by 9 is 174. We plot our 2 points, draw our line between them, and you can see it slices off some of the feasibility range there at the bottom. And that's what we were looking at when we were doing the intuitive method. We were limited by labor to only 174 when x2 was 0. Which is the case right here. You can actually graphically see that limit. So all this shaded area is the feasibility, the range of feasibility. And lower bounds, which are the 0, we can't make less than that. Those are just in there. So that's why we're only dealing with this positive quadrant. And then finally the tubing constraint, 12x1 plus 16x2, substitute 0 in for x1, solve for x2, you'll get x2 equals 2,880 divided by 16. That gives us 180. 0 and 180, that's 1 point, and then do the reverse on the other. We can draw our line, and you can see it slices it again. So that's our feasibility. Our feasible region has decreased further. So This is called solving it graphically with level curves. We're now going to plot our objective function. So here's our objective function. 350x1 plus 300x2 equals 35,000. Where did the 35,000 come from? It's just we made it up. We could make up any number we want. It's going to be linear. So any other, if we increase it, for instance, which we'll do next, it's still going to be a horizontal line. It's all going to be horizontal to this line. So this is just a random line that we're drawing. We just chose a profit of 35,000. We don't know. We want to have the maximum profit, but we don't know what that amount is. So we're just guessing 35,000. And then we're plotting it. So let's see, we're choosing 0 for x1. And then we have, that leaves us with 300x2 equals 35,000. Divide both sides by 300. You'll get x2 equals 116.67. Plot that. And then do the reverse. Put 0 in for x2. You'll get 350x equals 35,000. Now that's an easy one. Divide 35,000 divided by 350. You'll get 100. And that's our other point down there at the bottom, 100, 0. So those are our 2 points we can. Then we do one more line. Again, this one's going to be 350x1 plus 300x2 equals 52,500. 52,500, where'd it come from? We just pulled it out of thin air. We could have chosen 1,000,000, except that would be way out of the feasible range, so we want to stay kind of in the area. Substitute the zeros in, solve, plot our next line. It's horizontal. And what we can do is we can extrapolate out. We know that any amount of profit is going to be horizontal to this line. And what we want is the optimal solution. The optimal solution is going to be on the far end of the feasible range. So it's going to pass through the maximum amount. We can do that and figure out what's our optimal solution. The optimal solution occurs where unless there are multiple points, that's a different thing, so it caught me there. This occurs where x1 plus x2 is 200 and 9x plus 6x2 is 1566. Those are our two lines. From one we have x2 is, so we're trying to move the x1 over to the other side. We have, if we solve just for x2, the top equation, we have x2 equals 200 minus x1 because we subtract x1 from both sides. And then we can take that and we can substitute that in for x2. And then we have 9x1 plus 6 times 200 minus x1 is 1566. And that reduces down to x1 is 122. But we're solving for x1. It's kind of tedious, but the optimal solution is x1 is 122, x2 is the optimal solution is make 122 of x1 and make 78 of x2. So we get $350 profit for every x1, so 350 times 122 of them, plus $300 profit for every x2, so 300 times 78 of them. That gives us 66,100. So the optimal solution will yield us a profit of 66,100. The intuition method that we used earlier, it came out to about 60,000. Hey, let's just make as many of the higher profit ones as we can. Well, that yielded 60,000 something more. So you can see it's a lot more. It can really be valuable to make a better decision mathematically than to just use intuition. Sometimes intuition gets you the right answer, especially if it's a simple problem like that. Maybe we could use intuition to get a better number, but the more complicated it is, intuition just isn't going to cut it. So we want to, if it's a structured problem and we don't have to use intuition, which is guessing, why would we want to do that?